Hello everyone, welcome to the first lecture of week 11. In this lecture, we will explore different integrals, the basic definition of the different integrals as well as some of the examples, and then we will look at that how it differ from the regular integrals. So, let us start with the different integrals. Different integrals has the history itself, and it has been started as the antiderivative of the function. So, let us start. So, I will start from the history of integral, then integral of a function, then different integral and properties of some of the properties of the different integrals. So, what is the history? As you can see here, the Greek mathematicians Eudoxus and Archimedes developed the method of exhaustion or to find the areas and volumes of a given function, or it's look like it is just a primitive of the integration. So, it's just a behind of the integrations. And in the 17th century, one breakthrough has been came out by Cavalieri, and in regard of or in the honor of this Cavalieri, it is also called the Cavalieri's principle. Then he introduces a method resembling integration by summing infinitesimal slices. That means the sum of all infinite terms. So, integration is nothing but integration looks like as sum of the infinite terms. And as we all know that Isaac Newton has invented calculus to develop his gravity theory in 1600, and Leibniz was the first one when he introduces the symbol integral sign, and calculus as well. So, Leibniz introduces this integral sign, and Newton linked integration with physical concepts like acceleration, speed, motion and so on, and velocity and as well. So, how we can define integration formally? So, differential coefficients of a function fx is fx, capital Fx, then that means dfx by dx equal to capital Fx. See, capital Fx is the derivative of the function fx. Then this capital Fx, if you are taking this integration, that means the antiderivative, we say that fx is an integral or a primitive of capital Fx. So, if you are taking this capital Fx, integration of this capital Fx, this will give you the Fx. So, and what was the Fx? D of f by dx, that will be capital Fx. And now, if you are taking integration of capital F of dx, that will give you f of x. So, it's look like we had used all the time as a opposite to each other. So, in the sometime we call derivative of the function and integration as the antiderivative of that function. So, later x in dx is the variable with respect to which we are going to perform our integral sign, and capital Fx is called integrand, right. So, what is the different integral? That was the regular integration. You do not find out any boundaries here. So, what is the different integral? Different integral is denoted by an integration from a lower bound to upper bound and fx dx, where a is the lower bound and b is the upper bound, right. Sometime a is called lower limit and b is called upper limit of fx dx, and it is evaluated in two ways. Firstly, we have to evaluate if integration of f of x dx is equal to capital Fx, then the integration different integral a to b fx dx can be written as capital Fb minus capital Fa, right. That is the first way to find out the different integrals, the evaluation of the different integrals. And the second one is the different integral as the limit of a sum. We will explore this limit as the limit of a sum in a next lecture. So, in this lecture we are going to concentrate on the different integral only. And here is the in the slides, as you can see, each one has been defined differently and independently. So, this is the integral sign, and a is the lower limit of integration, b is the upper limit of integration, a small fx is the integrand, we call it the integrand, and dx is the infinitesimal change in the x, we call it the variable of integration. So, x is the variable of integration, and this is the whole is called the integration from a to b, right. So a different integral looks like in the same way as it has shown on the slides. So different integral, how to define different integrals in a mathematical way. So if a function f is continuous at every point in a closed interval a b, so you have taken a function in a closed interval a to b, and a capital F is any antiderivative, right, of this small f on this ab. So f is the continuous function and capital F is the antiderivative. That means capital F is nothing but it is del f by del of x, right. Then the different integral of a to b fx dx is equal, this is the derivative. So capital integration is fx of dx is equal to capital F, right, and f of b minus f of a. So we had done previously here. See here, a small a to b fx dx is equal to fb minus fa. So we are going to use this one. A small fx of this is equal to capital B minus of capital Fa, right. So a small a to b fx dx can be written as the value of this antiderivative capital Fx and from limit a to b. So that will give you capital Fb minus capital Fa, and where capital Fx is nothing but it is the derivative of that function is going to be the small function. So we are using capital F by capital X equal to fx, then this integration a to b small f dx is equal to capital B minus of capital A, and that's why it is sometimes called antiderivative, because this is the derivative of the function and you are taking that the antiderivative of this function, this will give you the integration, right. So let me explain with the examples. So find out, evaluate the integration 1 to 5x dx. So here f of x is given. F of x is how much? It is given as 5 of x, right? And I want to calculate from a lower limit 1 to 5 and this f of x dx, right? So I have to find out some of the capital F so that I will look like, so I am interested to find capital X. And what was the capital F? Capital F was nothing but in such a way that I will find out f of, and this f of x equal to 5 of x, right. So what was the function capital F which give me the 5x? So now look like this one, as you can see here, d of 5 x square by 2 and then d of x. This will give me 5 of x, right. So this function 5x square by 2 is my required capital F, and I will find out this f of 5. So capital F of x is nothing but it is 5x square by 2, right. So that is how the idea has been evolved with the time for a different integrals. So now I have already find that what will be my capital F. Capital F equal to 5x square by 2. So I will find out capital F5 minus capital F1. So putting all these value, you will find out the 60 is the answer, right. So that's once you will find out the capital F, it will become easier to find out the values of Fb minus Fa. Similarly, pi by 6 to 2 pi by 6 sin x dx. So I knew that if I have a d of minus of cos x dx and I want to take it as a derivative, it will give me sin of x. So that means minus cos x is my required function, that means the antiderivative of this sin x. So and taking limit from pi by 6 to 2 pi by 6, it will give me 0.866. So here is the geometrical meaning of this different integral. So 0 to 2 pi sin x dx, that is equal to minus of cos x, because antiderivative of sin x is minus cos x, and it will gives me 0, right. So integration from 0 to 2 pi is going to be 0, but can we find out the total area? So see, the value of different integral leads to 0, but the area as you are looking here, so see here the area is 2 here in the upper side, this one, and in the lower side area is also minus 2, but area must be in the positive sign, and henceforth you have to take the area as the modulus sign, and that will give you 2. So 2 plus 2 equal to 4. So even though you had find out the different integral as a 0, because the sign of the integration, the function and the axis, between the axis, as you can find out, this is the positive, this is the negative, and the both are making this one, so that is equal to 0. But the area of those, total area of the functions with this axis going to be 4. So sometime evaluating a different integral as the area of some function enclosed with the axis and the function is going to be wrong. So it must be, should be taken care for area and the different integral. Both are somehow difference with the sign. So these are the properties of some different integrals. I will show you with the geometrical interpretation as well. So order of integration. So if you have integration as a to b f of x dx, and if you want to change this order from the lower limit to the upper limit and upper limit to the lower limit, that means I am going to interchange with the lower limit to the upper limit, right? And this will happen, you can do this with the opposite sign. So if you are taking from a to b fx dx, it is going to be minus of b to a fx dx, right? So that is the one thing. The zero width interval, that means if you are not given you any width, so b equal to a, if you are taking b equal to a, so there is no width, right? So from the same fixed point to the same fixed point, so lower limit as well as the upper limit is going to be equal, then in that case whatever the function it is, it's going to be 0. So there is no need to evaluate any function, whatever the function it is going to be 0. And if you are multiplying any function with some constant and taking from different integral a to b, then the constant can be taken outside of the integral sign, and it will become k into integral of fx dx a to b, right? Similarly, you can add or subtract two functions, the integral of the two function, and it will going to be the individual of those type. So if I want to evaluate from a to b f plus of g dx, right, and this will give me the individual sum. So a to b f dx plus of a to b g dx, right? And similarly, you will have to find out the differences of this one. And again, the additivity, look at the fifth property. This will be a good one, and this will be a very applied part of the integral properties. So frequently we are using this one. So what it says that if you want to calculate from a to c, and there is a point b here, then you can calculate this one from a to b and then b to c. So here it is, right? So function is the same one during the whole interval a to c, and you want a different integral from a to c. There may be breakdown from between these two a to c. So b, b1, b2, b3, b4. You can have the finite breakdown here as well. So as you can see here, a to b can be and b to c. So this lower limit and this upper limit is the same one. B to c can be written as a to c, right? A to c. Similarly, maximum mean inequality. If f has a maximum value, maximum f, and minimum value, minimum of f, on a closed interval a b, then minimum f of b into b minus a is always less than or equal to the integral of a to b of fx dx, and this is always less than or equal to maximum of f into b minus a. So this is the difference, the length of the given closed interval. So this is b minus a is here, and this is the minimum value and this is maximum value, and you have an integration here. So domination, that means fx is greater than or equal to gx on ab, then the integral function is keeping their own domination, that is the inequality sign all the time, right? So if fx is given as the greater than the gx, another function of continuous function in a closed interval ab, then integral of AB is also greater than or equal to integral of Gx. Similarly, Fx is always positive or non-negative, you can say, greater than or equal to 0 on a given closed interval AB, then A to B Fx dx is all the time is greater than or equal to 0. This is the special case, as you can put Gx equal to 0, this will give me the same function, right? So if I have f of x is greater than or equal to Gx, and if I put Gx as a constant function 0, so this means give me f of x dx is always greater than or equal to 0 dx, and this will going to be 0. So that's how this is the special case. So these 7 properties you have to always keep in mind, so that whenever the integration come in a geometrical problems or in some trigonometrical problems or somewhere where you need the inequality or you need to find the different integrals as the area, then this will help you to evaluate those problems. And these are the geometrical interpretation of these property. The first property was 0 width interval. So if I choose a the lower limit as well as the upper limit, that will going to be 0, right? Similarly, constant multiply. If there is a function curve fx is here, and if I multiply by 2, so obviously the whole integration has been multiplied by 2. As you can see here, the area become the double one. So that's why k into fx dx integration a to b is equal to k into integration of fx dx. Similarly, sum. So if I have y equal to fx and y equal to gx, and if I want to evaluate integration of fx dx, as you can see here, these are the two one, right? So if I want to sum, then the individual sum is also going to be the same one, right? Similarly, additive of for a different integrals. So here a and c are the two closed interval points, end points of the closed interval, and b is the midway or somewhere lies between the a and c. Then the integration a to b fx dx is equal to integration b to c fx dx. So that is the same thing. Similarly, maximum minima has been plotted here, as you can see here, and then domination is also plotting here. So these are the geometrical interpretation of the properties. You just go through it, and once you go through it, you will see that these are the property where everything depends on the meaning of the area of the curve enclosed by the function. So now there are other several properties, and we want to prove those property. So one property is here. If I change this argument x into t, what happened? There is no changing of the variables of a integrand. So if you have an integrand capital fx dx, and if you want to change this integrand value as a capital Y dy, that will be the same one. There is no differences at all. So the different integral give you the properties that if you are changing the integrand variable of the integrand function, that will be okay. There is nothing to be changed and nothing to be worried about the value of the integration. So now I have to prove that a to b phi x dx is equal to a to b phi t dt. And how I have to prove that? So suppose phi x dx is equal to capital fx plus c1. Now it is suppose, let this one will happen, right? Thereby phi t dt equal to capital ft plus c2. Therefore a to b fx ds is equal to fx plus c1 a to b, right? And that will give me, since it is a constant function c1, this will give me fb by minus fa. Similarly, this is the c2 as the constant function. So different integral give you the reflexibility or flexibility to choose such type of variable change. So fb minus fa, both are the equal, and henceforth a to b fx dx is nothing but is equal to phi t dt. Similarly, property 2, a to b phi x dx can be written as minus of b to a phi x dx. So I have to show that order of integration can be changed by opposite signs. So let evaluate the left hand side. So I am going to evaluate minus of b to a phi x dx. that can be written as let this integration phi x of dx is equal to capital Fx. So, Fx plus c some constant and b2a, that will give me Fa plus c minus of Fb plus c. So, that will give me minus Fa, and this minus minus become the plus 1. So, this will going to be plus Fa, right, because this minus and this minus makes it positive 1. So, that means this is nothing but Fb minus of Fa, and this is nothing but a to b phi x of dx, right. Similarly, let us see property 3. So, we have to prove that a to b phi x dx can be written as a to c phi x dx plus c to b phi x dx. So, let from the right hand side evaluate the right hand side and evaluate in such a way that it is equal to where? It is equal to the right hand side. So, phi x dx can be written as phi x plus c a to c and c to b. Just simplify it and this will give you Fb minus Fc. So, that it is not c but it is going to be a. So, this will be equal to a phi x dx, right. I mean, as you can see here, Fc cancel out and you will have this one only, right. So, it's a typo here, this is Fa, right, and that means the third property is proved. Based on these property, now we have a very simple examples. Evaluate the first example, the integral as 0 to 5 integration of x dx, right. So, I equal to 0 to 5 greatest integer x dx, and as you can see, the greatest integer is always defined on the integers, the discontinuity and the integer, right. So, that will give me 0 to 1, how much the value of this? This is 0, and 1 to 2, that will give me greatest integer as 1, greatest integer at 2 to 3 is 2, and greatest integer at 3 to 4 equal to 3 and so on, right. So, I mean the last one is the 4 to 5 as a 4. Evaluate all those and it will give you 10, right. So, I have used which one? I have used a to c f of dx is equal to a to b f of dx plus of b to c f dx, right. So, these are the quite easily proven or giving me the solutions of the problems even if I use the property of the integration. Now, the fourth property, that is important property, a to b f x dx can be written as a to b f a plus b minus x dx, right. So, that means a plus b minus x dx. Now, here x was the only variable and here the argument has been changed as the limit, sum of the limit minus of x dx, right. So, to prove this property, let us suppose that a plus b minus x is equal to y and take the derivative both sides. So, this is minus dx, this will become dy. Now, you can see when x equal to a, now I have to change dx, right. So, x equal to a, what will be the y? Y will be in place of this. So, a is cancel out, y will be b, and if x equal to b, the y become a. So, now I have to change this whole integration and this will comes out to be b to a f by dy, and what was given? A to b f x dx, and now we have find out here as b to a f y dy. So, using the two properties at the same time, right. So, this will give you, I mean both integration are the same one, right, because we had already done as phi x dx a to b is equal to a to b phi t dt, and as well as we have seen that phi x dx can be written as minus of b to a phi x of dx. So, these two property you will see that we have the same value, right. Similarly, this one of the example using the property 4, and it will comes out x into 1 minus x to the power 99, that can be written as a plus b minus of x, right, and use this property and this will give you 1 divided by 10,100 and so on. Similarly, now property 5, a to b phi x dx, that is equal to 0 to a phi a minus x dx, And how we can write this one? So the right hand side, as you can see here, 0 to a phi a minus x dx, and put a minus x equal to t, then dx minus of dx equal to dt, and for upper limit x equal to a, t becomes 0, and x equal to 0, t become a. So this will be the same one, and henceforth this will hold, right? Using the property, this will be hold, right? And using the property 6 is also given. 0 to 2a phi x dx can be written as 2 into a to b phi x dx when phi 2a minus x equal to phi x. See, and this is equal to 0 if phi 2a minus x equal to phi x. So using from the left hand side is given 0 to 2a. This can be written as 0 to a and a to 2a, right? We have find out 0 and 2a, so we are putting a as a value. Now consider 2a minus x is equal to t, so this will give you minus dx equal to dt, and as x equal to 2a, t becomes 0, and x equal to a, t become a. And using these one now, so a 2a phi x dx become minus of a 0 phi 2a minus t, and as you can evaluate this one, 0 to a phi 2a minus x dx. So LHS 0 to a, that is the right hand side, right? So it will become the right hand side now. So LHS become the right hand side one. So that's the proof. So property 7, minus a to a fx dx equal to twice 0 to a fx dx when function is even, that means f minus x equal to fx, and 0 when function is odd. And the proof is as similar to the previous properties. Using those property, you will see that the proof is easy to go. So go through these proofs as it has been elaborated using the more and more functions for you. So go through it, you will find out that this will be easiest one. Now this is the one example where you have to apply these properties. So evaluate I from this is the lower limit and this is the upper limit. So a is given equal to minus 1 by 2, b equal to 1 by 2, and the question will be asked a to b cos of x log of 1 plus x divided by 1 minus x modulus, right? Evaluate it, you will find out that this fx, find out f minus of x, and this will be f of x become minus of cos log x. So as you can see, this is the odd function, and once it is the odd function, then what will be the property? The property says that the value is going to be 0 here. See, minus a to a 0. So we have to evaluate here minus 1 by 2 to 1 by 2. You don't have to just go through the evaluation of the integration. You need to understand the properties. Those properties will help you to make the problem much easier, and the solutions will come out very easily. So as you can see here, minus 1 by 2 to 1 by 2, this will be nothing but this is minus a to a f of dx, and f is the odd function, and we know the answer, this is equal to 0. So without any evaluations, you will find out the answer, right? So I think this will be the end of this lecture, and I believe that once you go through it, this will makes you more and more accommodate with the different integrals. So thank you so much.